but the UK bureaucracy won, so that didn't happen. So I guess we'll have to make this do. I know watching Zoom talks is less exciting somehow usually, but hopefully you'll bear with me for these several lectures. So the topic of my mini course is, I guess, model theory and combinatorics. And by the way, can everyone see what I'm writing here? Yeah, okay, great. Okay, so let me maybe say a couple of words. What is the connection really? I mean, by now there are, of course, multiple connections between these two fields, and I'm going to focus on a certain subset of the recent developments, reflecting some kind of philosophy, I guess, or connection between asymptotic questions in finite extremal combinatorics and model theoretic classification theory. So pure model theory, classification theory in the sense, I guess, of Sherlock and others. Okay, things like stability and IP, etc. So how do finite sets enter the picture? So the goal, what we will be typically interested in is understanding how when we're given a family of finite subsets of a model of a first order structure, how these finite subsets asymptotically interact with definable sets in the structure. Yeah, so somehow we have this nice category of definable sets, and then we have some given, let's say, sequence of arbitrary finite subsets of the structure. And we will try to understand how various model theoretic tameness assumptions like stability and IP, etc., or minimality, yeah, for those who prefer that, how these tameness assumptions restrictions on how finite sets interact with definable sets. So a typical picture will, just to give you some more like motivational words, or maybe some more words about the context. So typical picture will be that we have a sequence, let's say mi, indexed by some ordered set capital I. So this will be typically a family of structures in some fixed language L, a family of L structures. And in fact, very often we will be in the situation that this is just a single structure. So typically mi will be just the same structure M for all I. Okay, so we're given a family of structures like this, and assume that for each I, we have some finite subset of the model. So let's say AI subset of mi, a finite set for each I, okay? And so what we're trying to understand is how this sequence of finite sets interacts with definable sets in this L structure. So typically we'll take M to be the ultra product of all these MIs with respect to some ultra filter, yeah, usually non-principal to keep it interesting. So for U, some non-principal ultra filter on I. Okay, and so once we have such an ultra product, we can of course form also the ultra product of this finite subsets. So similarly, we can let A be the ultra product of the AIs, okay, which is now going to be an infinite set typically. So to avoid triviality, we can assume, let's say, that the sets AI are growing in size. Yeah, so let's say AI grow in size with I. Okay, and so we have this A, a subset of M. Now, what can we say about the behavior of this ultra product of finite sets? So this set is now what is typically typically call it a pseudofinite set, an ultra product of finite sets. Yeah. So in finite combinatorics, we're usually interested in counting things, so we are not really interested in the exact set A, somehow this asymptotic shape of our family, but rather we're interested in some of its structural properties, such as, and I say some vague words, but with time we'll see precise meaning of these words. So something like the density of this set, or the measure of this set, or the dimension of this set. So some of these global properties of this infinite of this finite family of sets. Okay. Questions? Yeah. Sorry.
No, you lagged briefly.
Okay. Yeah. Can you hear me now?
Yes.
Okay. Yeah. Okay. Sure. And yeah. So feel free to ask questions at any point, I guess, to interrupt me. Okay. All right. So we have such a set, right? So there's an obvious parameter that we can associate to this set. So namely, for each I in our index set. By the way, this index set is typically going to be countable. Yeah, we are not. So you can just think it's the natural numbers, the index set. So for each I and formula, phi of, let's say, xy in L, and a parameter b, let's say bi, an element of the model mi, where it corresponds to the variable y, we can consider the number, we can consider mi. Yeah, so we can take this mi of phi of xbi to simply be the cardinality of the set of elements inside the I which satisfy this formula. Okay, so this notation, by this I simply mean the set of all A in AI, so that mi satisfies phi of ABI. Okay, so we have a family of definable sets with parameters, and we look at what they cut out from our given family of finite sets AI. Okay, so of course it's a finite number, right? Each set AI is finite, and then we can take the limit. So we can take m of phi of xb to be the ultra product, well, the element in the ultra product of the mi's. Okay, so we can take it to be mi I and I modulo the ultrafilter u, right? So it's an element of the ultra product. It's an infinite sequence of natural numbers. All right. So yeah. So it's in other words, you can think about it as a non-standard natural number, which is in particular a non-standard real number in the corresponding ultra power of the reals. Okay, so given a family of finite sets, we can associate to it this number, this non-standard real, which somehow reflects this asymptotic behavior of the sizes of the sets, right? Well, modulo ultrafilter, so we were always willing to ignore, let's say, some finite chunk, but somehow we hope that this number reflects a lot of information about the size of our sets. In fact, it reflects too much information typically for it to be useful. So what we try to do is usually extract some more structured information from such a number m associated to a family of finite sets. And there are two main notions which arise when we try to do it. So when we're interested in different scales at which these sets can grow, we talk about dimension. Okay, so from this number, from m, we can extract two things. So the first one is dimension, and I put it in quotation marks. So this will be the topic of the second lecture, in fact, dimension, or pseudofinite dimension. So this is when we want to compare sets of different size or different scales. Yeah. So for example, we want to compare sets of the form, let's say, growing as n to some power c and n to some power, let's say, c prime, for c different from c prime. Yeah. So by this I mean that the size of, let's say, an, if the size of an, for example, looks like this, Yeah, so some polynomial of some fixed power, or if we have some different power. So when we have this drop of power between in the asymptotics, here usually the dimension comes into play. Or we can talk about sets of the same scale. So this corresponds to measure, and this is the topic of today's talk. Okay, so this is when we want to compare a size of roughly the same scale at the level of the exponent, but when the constant is different. So here we want to compare sets of the form something like c times n to the fixed power d and c prime times n to the power d. Yeah. So the exponent d is the same, but the constant varies. Yeah. So somehow the fraction varies, and this corresponds to measure in the ultra product. And so that's what we are going to talk about today. Or more specifically, we'll talk about so-called Kisler measures. Okay. So all of this is a bit vague, but hopefully maybe it gives you some intuition where we are going with all of these things and what they have to do with combinatorics at all. Because for a minute now, we will just focus on purely on measure theory and model theory. Okay. So I'm going to switch to the next slide unless there are any questions about this this hand waving part. No, okay. All right. So then let's talk about Kisler measures. All right. So the situation here is the same as always. So we fix some first order theory T complete to avoid some complete pathologies. So complete theory. Everything is first order in this talk, by the way. Yeah, first order theory. And let's say M is a monster model. Actually, yeah, let me try to write it as bold M, boldface M. So M is a monster model of T. So, but if you're not familiar with monster model, just saturated model, or sufficiently saturated model. All right. So we're in this situation, okay? Now, definition. So let's define the main object of our conversation today, Kisler measure. So a Kisler measure, and in the future, I might omit saying Kisler every time when there's no confusion about the context. So a Kisler measure over a set of parameters, A, inside the model, yeah, in variables X. So we fix a tuple of variables, okay? So this is simply a finitely additive probability measure on the Boolean algebra of A definable subsets of M to the power X. Okay. So we fix a tuple of variables and we look at all definable subsets with parameters from A of the corresponding power of our model, of our structure M. Yeah. So of course they form a Boolean algebra. So it makes sense to talk about finitely additive probability measures. So let me remind what this means precisely. So this means that for every formula, phi, let's say phi of x, a formula with parameters in A, because I'm going to basically identify formulas and sets that they define in this model. Yeah. So for every formula, let's say this measure mu. Okay. So this mu satisfies the following. So we have that the measure takes values in the interval 0, 1. So mu phi of x belongs to the interval 0, 1. Yeah? This is the part saying that it's probability measure. So the top measure of the whole space is 1, which we can equivalently write the measure of the formula x equals x is 1. Yeah. It is finitely additive. So meaning that we have for any, let's say, 2 phi of x, psi of x, both formulas with parameters NA, which define disjoint sets. Yeah. So such that we have phi of m intersection with psi of m is empty. Yeah. And by this again, I mean the solution sets. So the set of all elements of the model satisfying this formula. Yeah. So if given two disjoint definable sets, the measure of the union, so measure of phi of x disjunction psi of x, is just the sum of the measure of their respective measures. So mu of phi of x plus mu of psi of x. Yeah. And I guess I should also add that the measure of the empty set is 0. Okay. So note that here we only require finite additivity since we are working in a Boolean algebra as opposed to working in a sigma algebra. But this is not going to be like a serious problem for us if you are used to normal measure theory. I'll remark on it in a second. So let's begin with a couple of examples of Kisler measures. So the very first example for a model theorist, I guess, is that every type is a Kisler measure. So every type P with parameters in A, yeah. So and variable x is a Kisler measure like this. Yeah. So we view it as a measure by identifying those sets which are in the type to have measure 1 and those sets which are not in the type to have measure 0. Yeah, so it's even takes values in 0, 1. Right. Okay, so types are in particular measures, 0, 1 measures. So it's a very natural generalization of types, but of course in the world of measures, we are also allowed to take convex combinations. Right. So namely, if I have some sequence of numbers, let's say AI, which add up to 1, let's say I in omega, for all AI in the interval 0, 1, I guess, and we have mu I, some Kisler measures. Oops. So mu I Kisler measures. Then we can take the convex combination. So then we have that the sum, so we define now mu to be the sum of AI times mu I for I and omega. So this is also a Kisler measure. All right. So we're allowed to take convex combinations. In particular, each of these mu i's could be a type, which is an interesting case, or it can even be just an element of the structure, right? So we can take averages of elements in the structure in this sense and view them as Kisler measures naturally. Okay. So another example is the pseudofinite measures, which we discussed earlier. So namely, given AI contained in MI finite sets, as so the same setup as we had on the first slide, we can define mu of phi of xb to be the ultra limit of the cardinalities of the set of realizations of phi of xbi in AI normalized by the cardinality of AI. Okay. So what we can do, is take the ultra limit of the normalized cardinalities of the finite sets in a given family. And this again gives us a Kisler measure. So
you need a standard path, right?
Excuse me?
You need the standard part?
Here I don't, but we can define it using the standard part. So here I'm actually taking the ultra limit, right? So this is an ultra limit of a sequence of real numbers, bounded sequence of real numbers in the interval 0, 1. So the ultra limit always exists, and it's an actual real number. But indeed, we can also define it differently, and this is the same thing. And maybe this could be an exercise, or if you're familiar with one of the two of these two settings. So alternatively, we can take the standard part. So we can take the standard part of the non-standard cardinality, right, resulting from this. So we can take the standard part of these cardinalities. So phi of AI bi over AI for I and I modulo the ultrafilter U, right? Yeah, so this is the number M that we have, well, not exactly M, sorry, this associated to this non-standard number M that we had on the first slide. So these two actually give the same result. And also, yeah, one has to check that the result is indeed a measure. Yeah, so it's finitely additive, etc. So this is a good exercise to get a bit accustomed to this kind of notions. Yeah, but this is a very important example. In fact, this ultra product measures, the pseudofinite measures, which is kind of the key to the connection between combinatorics and infinitary model theoretic results that that we like to combine. So this is an important example which connects asymptotic growth in the finite at the level of the measure with some qualitative behaviors of the ultra product. Yeah, so this is some examples. Let me give you one more example for, so whenever we're in a situation, so for example, let M be no minimal expansion of the reals. Let's say M is an expansion of the reals, the field of reals. Assume this is O minimal. Sorry, and what I wrote here, so it's both an expansion and an extension, right? So take your favorite O minimal expansion of the field of reals, and then you can take an elementary extension. Okay. Then we can define we can use the Lebesgue measure to define a natural Kisler measure associated to it. So let lambda be the Lebesgue measure on the interval 0, 1, let's say, in the actual reals, yeah, in the standard reals. And then we can define mu of a formula phi of xb to be the measure of phi of m. So okay, so I have this curly m here. So phi of mb intersected with the interval 0, 1. Okay. And where lambda is again just the classical Lebesgue measure. And by minimality, this definition makes sense. So this is a small exercise to verify. Yeah, by minimality, every definable set is just a union of intervals and points. So of course it's Borel in particular. And so it makes sense to take this measure. It's a measurable set, Lebesgue measurable. And this way, we define a Keisler measure on the definable subsets again. And normalizing on the interval is what ensures that we get a probability measure in the result. Yeah. So okay. So this is another example. Similarly, if you have some, let's say, definable group equipped with a higher measure. So for example, we have a compact group in definable in some structure. Again, naturally, it gives rise to a Keisler measure associated to it in this manner, assuming the definable sets are measurable with respect to it. Yeah. So it's a general construction. All right. So, and finally, let me give you just one more example of a measure, kind of measures which behave very differently. Assume we have a random graph or a generic graph. So let M be, let's say, the underlying set M, and I have an edge relation, be the generic Rado graph. So this, for those familiar with the notion of Fresnel limit, this is just the Fresnel limit of all finite graphs. Otherwise, it's just a countable graph where, given any pair of vertices, you flip a coin with probability 1/2, and it decides. Yeah, the generic Rado graph. And we can define a measure, again, on definable subsets.
Could
So
you just
namely,
repeat that definition you cut out for it? For the...
Oh, I'm sorry. Yes. So we can define this generic graph probabilistically. Look at the natural numbers and take any two natural numbers, which we think about as vertices of our graph, in order to decide whether we take an edge between them or not. Flip a coin with probability 1/2. Yeah. This decides whether you have an edge or not, and do it independently for any pair of vertices. Yeah. So this, as a result, this defines a structure which, up to isomorphism, is unique, countable structure, which is uniquely determined up to isomorphism by this property. All right. So now we can define a Kisler measure here, where, for example, if we have some Boolean combination of edges and non-edges, well, before that, let me stress that this is quantified elimination. Okay, so all formulas are just of the form X is connected to Y or X is not connected to Y, and Boolean combinations of such formulas. And so we can define a measure, which, let's say, if we have a definable set defined by the condition that X is connected to some AI, but maybe not connected to some BJ, let's say. Okay. Then we can define the probability, the measure of such a set, to be 2 to the power minus the cardinality of I plus J. Okay. So each condition being connected to a given edge or not connected to a given edge has probability 1/2. Yeah. And because of the quantified elimination, this defines a probability measure on all definable subsets, because all definable subsets are of this form. Well, you also have equalities, so I'm being a bit floppy here. Yeah, you can also have forms of the form like X is equal to Y or not equal to Y. Yeah. Well, let me not focus on that. And I also should say probably here that these are pairwise distinct, all pairwise distinct elements. Otherwise, it would be contradictory definition. Okay, so this way we can define a measure. Okay, which is again a Kisler measure, of course. Yeah. So, and this example will illustrate some phenomena very different from the ones that happen in NIP structures or in stable structures. All right, so these are Kisler measures, the definition and some examples. Now, let me address the remark I have made earlier that we can connect these finitely additive measures to the usual countable additive or sigma additive measures in a natural way. So remark, every Kisler measure mu, let's say, extends uniquely, extends uniquely to a regular probability measure on the Borel subsets of the space of types. So how do we view this? Yeah. So if I'm given a Kisler measure, it assigns a measure to each formula, right? But if you remember the topology on the space of types over a given set of parameters, it has a basis of clopin sets, right? So this topology has a basis consisting of clopin sets, and each clopin set can be identified with a formula, right? So each formula corresponds to a clopin set, namely all types to which this formula belongs. Yeah. So then Kisler measure automatically can be viewed as a measure on the Boolean algebra of clopin subsets of the space of types. Okay. And then using Karateodoris theorem, so this is by Karateodoris theorem, a basic result in measure theory. I'm probably forgetting some accent somewhere. Apologize for that. So by Karateodoris theorem, if you, in such a situation, you can extend it to a countable additive measure on the sigma algebra generated by the clopin sets, which is precisely the Borel subsets here. Yeah. Let me just remind what regularity means. So a measure is regular. So regular means that for any Borel set X, for any Borel set of types, yeah. So the measure of this set X can be obtained either at the supremum of the closed subsets. So this is the supremum of mu of C for C subset of X closed. Yeah. The same as the infimum of mu of O, where O is an open superset of X. So the typical condition one wants to impose when working with measure in measure theory. Yeah. So it's a technical condition. Let's not focus on it too much. But there is this unique correspondence. Yeah. So there's this unique extension, and so each Kisler measure can be naturally viewed as a sigma additive measure on the Borel subsets of the space of type. All right. And in fact, this gives us an affine homeomorphism between the space of Kisler measures and the space of Borel measures on the space of types. So this duality sometimes comes into the picture, but yeah, let me just, I just wanted to point it out. Okay. The last property, I guess, is of the collection of all Kisler measures. So they also form a space themselves, naturally. So definition. Let us denote by mx of A the space of all Kisler measures over A. Yeah. And when I say space, we need some topology, right? So we can topologize it by taking the restriction of the product topology. So with the induced topology, from the product space, we take the interval 0, 1, and we take it to the power given by all definable subsets of A with the product topology. Okay. So we take right, because what is a measure? So the measure is an assignment to each definable set. We assign a real number in the interval 0, 1. So we can view measures as functions from formulas into 0, 1. Hence elements of this product space. Now, of course, by Tikhonov's theorem, this is a compact space, the product space. And so it remains to observe that the space of measures, the subset of measures in this set, in this space, excuse me, is a closed subset. So note that M of X, A is a closed subset of the product space. Okay. So one just needs to check that the conditions on B in the measure define a closed set. Yeah. So let me leave it as a little exercise for you to check. And since it's closed, yes, so it's in particular, it's compact. So we have that this is a compact space of measures. which can be viewed against generalization of the space of types for a model theorist. In fact, types form a closed subset of this. So we also have that the space of types over A is a closed subset of the space of measures. Right, and we embed it naturally by identifying a type with a Dirac measure on it. Yeah, so remember, we already said earlier that each type can be viewed as a 0-1 measure. So by this identification, we see that the space of types embeds as a closed subset of the space of measures. Okay. Let me remark also, for those more familiar with measure theory, that what we get here, the topology that we get in this way, is the same as the topology of weak star topology. On the space of Borel measures associated to these Kisler measures, as I explained on the previous slide. Yeah. So even if we take this logic topology, just coming induced from the product topology, what we recover is the usual weak star topology on the space of measures. All right, so we have the space of measures, which can be viewed as generalized types. And in fact, that philosophy will work for some of the results we're going to establish later on. So, okay, so we have this space of measures. Now, the question becomes, what does it have to do with model theorem combinatorics, right? Once we have defined some of these things, I guess I need to formulate quickly a couple of properties of Kisler measures, which are generalizations of the corresponding properties for types that you might be familiar with. So let me define them. So one, given a measure mu in the space of measures over, let's say, the monster model or some saturated structure, we say that it is A invariant, whereas before A is a small subset of the model. So such a measure is A invariant. Well, if it's preserved by all automorphisms of the saturated model which fix A. So we have mu of phi of x, B, let's say, is equal to mu of phi of x sigma B for every sigma, an automorphism of M, an automorphism of M, which fixes the set A pointwise. Now, given an A invariant measure, we will say that moreover, mu is definable mu is definable over A if the assignment of the measure to a formula is a continuous function. So if when we look at the function, which takes a type of a parameter B and sends it to the measure of phi of xb, so this is a map from the space of types over A to the interval 0, 1. Yeah. So if this is a continuous function, for every fixed formula phi.
Artem?
Yes.
Sorry, I'm a little bit lost. So what is the measure on the monster model?
So we defined this over any set, right? So in particular, you can take the set of parameters. So this simply means that A is equal to the whole model M. Yeah, that's it. So it's like with types, you know, sometimes we can consider a type over a small set of parameters inside the big saturated model, or sometimes we can consider a global type, which is allowed to use parameters from the whole big model. And so here's the same, but for a measure, right? So we just allow we just say that the measure is defined on formulas with parameters anywhere in this big saturated model.
Thanks.
Okay. So we have this. Now note that this makes sense. First of all, this definition of definable measure, right? Because if it is A invariant, then like we said, the measure should only depend on the automorphism type of B over A, right? But in a sufficiently homogeneous structure, this means that the measure only depends on the type. So by invariance, by A invariance, we have that the measure of phi of xb only depends on the type of B over A, right? Because any two tuples of the same type over A can be sent by an automorphism one to another, by an automorphism fixing A in a homogeneous structure. So, right, so then this assignment is from types to real numbers. And when it is continuous, we say that the measure is definable. And if it's only a Borel map, we might say sometimes that the measure is Borel definable, a slightly weaker condition. Again, this corresponds to the usual notion of a definable type. If you're familiar with it, if our measure happens to be a type, this corresponds to just a type being definable. So for mu equal to a type, the usual meaning of definability. It's a little exercise to check this. Okay, so we have definable measures and invariant measures. All right, so, and finally, given a pair of definable measures, we can form a product of these two measures, which is going to be a measure in two variables. So given mu, a measure in the variable x, or a tuple of variables x, okay? And let's say nu, which has a tuple of variables y, we can form a product. So we define mu, tensor product mu, and this is going to be a measure in both variables simultaneously, yeah? So it's a measure in xy now, as follows. So given a formula, let's say phi of xb, phi of xy in two variables, let's say, yeah. Excuse me, let me erase it. Let me stress the parameter. So given phi of xyb now, so xy b, yeah, so we need to say what the measure of this is. So we're going to assign to it the measure to be the integral of mu of phi of x a b. Sorry, let me put here the type actually. Let me put p here, and I'll explain it in a second. So we have phi of x p b d nu, and here we integrate over all p types over a in the variable y. Okay, so we take the integral of this with respect to, of mu with respect to nu here. Oh, and this should be phi. Excuse me, what I wrote is nonsense. So this is phi here. Now, why am I allowed to put the type there instead of actual parameter? Well, by what we just discussed, right? So if the measure is definable, or even just invariant, we know that the measure here depends only on the type of the parameter, okay? And this, moreover, is a continuous function. So this means that this integral here makes sense because here we have a continuous function which depends on p, where p varies over types over a. Yeah, so we're just integrating a continuous function in this case. With respect to nu, where in this case we view nu as a Borel measure, as explained earlier. So the integral makes sense. It's the usual notion of integration, Lebesgue integral.
Excuse me.
Yes, question.
Don't you need P to be a type over AB?
Type over 1 second. Type over. Oh, of course. Thank you very much. I'm sorry. I wrote some nonsense again. Yes. So here we need. Thank you very much. Yes, we need this to be a type over AB. And this is still makes sense, right? Because if we knew that mu was invariant over A already, then it's in particular invariant over AB. So the explanation I just gave still makes perfect sense. But there's a little bit more to check. So you need to check that this somehow is indeed well defined. Yeah. So I can wait.
You just cut out again before.
Oh, okay. I'm sorry. So yeah. So I want to. I'm just saying that I'd like to leave as an. Can you hear me?
Yep.
Yeah. Okay. Yeah. I'm saying I want to leave as an exercise verifying the details of this definition, but like, oh, you can believe me, it makes sense. And if you're familiar with types, again, so what we get here is the usual notion of a free realization of types. So for types, so if let's say we have that we are given two types, P and Q, two definable types, or just invariant even, then P tensor Q is simply the type of the pair AB, where B realizes Q and A realizes P over, B realizes Q over A, let's say, and A realizes P over AB. So first you realize Q and then you realize P over it, yeah, and take the type of the pair. And so here, this is exactly what we imitate with this integration.
So we're taking, like, the product here is over this set A, like it having different.
Yes, right, but yeah,
give different measures.
Yes, but but to define a global type, the globe product, so the product of two global types is a global type. So here I just wrote it over A, but the same you can do over any set B containing A, right? And so this defines types over a bigger set of parameters. As a result, it defines a global type. So all of them are compatible. You can just take the union of those. And for measures, it's the same idea, yeah. That here, strictly speaking, I guess that's what you're pointing out, right? So here, what I really defined is mu restricted to A. And we can play the same game over any larger set of parameters which contains A. And this is how you get a global definition. This is how you get a global measure. Is this okay?
Yep.
Yeah, okay. All right, so we have this notion of a product of two Kisler measures. Important point, this product is not commutative in general. So the order in which we take the product matters. So note, for example, if I already at the level of types, this plays a role. So for example, if I have the formula x is less than y in DLO, okay, and take the type to be, let's say, at plus infinity. So let's say P says x is, by DLO, I mean dense linear order, right? So like just Q with ordering. And if I have the type which says I'm bigger than everyone, let's say, yeah, type at plus infinity, then we have that the order of the product matters. So if I take the product of P of X with P of Y, so I'm taking the product of the type with itself. It's not equal to the product of P of Y with P of X, right? Because one of them is going to contain the formula X is less than Y, and the other one is going to contain the formula Y is less than X. Okay, so of course this example is not stable, not a stable theory, and somehow an important property is when we have a measure which does commute, for which the product does commute. This is a special class of measures, so-called generically stable measures. So I'll probably mention more about that later. Okay, so finally, let me go back to combinatorics, or rather to a measure theoretic reformulation of an important result in combinatorics. So namely, I want to say a few words about Szemerédi's regularity lemma. Okay. Maybe I should pause and ask if there are any questions about this, about Kisler measures so far. Okay. If not, let me state a measure theoretic reformulation of Szemerédi's regularity lemma. So this is a result which tells you that asymptotically large graphs can be partitioned in a way so that outside of a small error, they behave like in a random manner, approximately in a random manner. But I want to state it in a measure theoretic version. So assume we have two Kisler measures. So we have mu of x, mu of y. Assume they're definable and commuting. So by commute, I mean in the sense of the tensor product. So in fact, I should say pairwise commute. By which I mean that we have both mu tensor nu is the same as nu tensor mu. Yeah, but also I want to say that each of mu and nu commutes with itself. Mu commutes with itself. Okay, so we avoid the situation that we had in the previous example. An important case to which this applies, and this is how you get the original Szemerédi Regularity Lemma from what I'm going to say, is that, for example, if mu nu are ultra products of finite counting measures. So pseudofinite measures in a sufficiently rich language. Okay, so what do I mean by sufficiently rich language here? By this, I mean that you're given a sequence of finite structures, and you assume that your language includes all subsets of those structures. You want that every subset is definable. So this is something like what you have in non-standard analysis, for example, that all subsets are definable, and then you take the ultra product and you get so-called internal sets, which are the ultra products, which are subsets of the ultra product, which are themselves the products of subsets of the sequence of which you take the ultra product. So if all of that is in your language, you're going to have this condition. Okay, so assume we're in this situation. Now assume you have an arbitrary definable relation. So let E of xy be definable. Okay, so I have a arbitrary definable binary relation. We can think about it as a bipartite graph, for example. Okay. Okay, so then for every epsilon greater than 0, arbitrary small real number, there exists some definable partition let's say V1 through Vn of the sort corresponding to the variable x. Similarly, we have W1 through Wn corresponding to the sort y for the variable y. Okay. So that we have the following situation. So first, there are some bad pairs in this partition that we have to ignore. So I'm going to define to say that okay, so that for some excuse me, let me rephrase it like this. So we have this partition and some bad pairs some bad pairs in this partition. So and let's say some sigma, a subset of n square, so that. So one, the total measure of the rectangles in sigma is small. So if I look at mu tensor nu, excuse me, mu tensor nu, and I look at the union of all pairs of the form Vi times Wj, for ij a pair in sigma, okay? So the measure of all of this is going to be smaller than epsilon. And about this we think as bad pairs, okay? But now, if I'm not a bad pair, so for any good pair, so for any ij not in sigma, we have that the edges are approximately uniformly distributed on this rectangle. So we have that if I look at the measure, so for any definable, let's say A subset Vi, B subset Wj, we have that if I look at the measure of the edges on A times B, okay, this is going to be approximately okay, so sorry, for any of these exists a number Dij, a real number, which represents the density in the interval 0, 1, so that the measure of the edges is approximately Dij, approximately up to epsilon, I mean, Dij times the measure of A times the measure of B. Okay, so if I want to represent it pictorially, imagine this is the incidence matrix of our graph. So let's say this is mx, this is my, okay, and I put a dot whenever I have an edge. Okay, so this is my graph somehow. So what I'm saying is that I can partition mx. So this corresponds to v1 through vn. I can partition w1 through wn. So this is a partition for the sort corresponding to the variable y. And after I throw away some bad parts, for example, I cut out this one, this one, this one. So I throw away some bad rectangles, but total measure of these rectangles is small, at most epsilon, within the error term. Yeah. Then on any remaining rectangle, the edges are distributed approximately uniformly. So meaning that if I take any subrectangle, like if I take some subrectangle of this, and ask how many edges I have on this subrectangle, the density is approximately the same as on the whole rectangle. Approximately again, meaning within epsilon. That's what you would expect if you just picked the edges at random, yeah, with the given probability. So this is Szemerédi's Regularity Lemma, the celebrated result from combinatorics, or more precisely, its measure theoretic formulation. There are many variants of this result, but I guess this is the simplest one to state. And let me point here how you get something interesting for finite graphs in the asymptotic region here. And then I'll stop. So I think I have to, yeah. So the point here is that here, look at the sequence of quantifiers in this statement. So I'm saying for every, so I fix my measures already, right? I fixed my measure space, and then I say that for every epsilon, we can find such a partition, which is finite, but I haven't said anything about this number n, okay? But thanks to a compactness argument, like logical compactness argument, we can actually reverse these quantifiers. So what we can show is that actually this n depends only on epsilon and doesn't depend on mu, nu, or e, yeah? So in fact, very importantly, n can be chosen to only depend on epsilon. And this follows by compactness, because if it was not the case, we could find a sequence of graphs and measures which would indicate that we need larger and larger n in order to achieve this result. But then we could take the ultra product of those counterexamples, which again would be still an object to which the theorem applies. Yeah, but existence of some finite partition like this for arbitrary measure spaces, so they could be infinite here. Yeah, like my measure space could be infinite. Existence of some bound by an ultra product argument or by compactness argument implies that in fact this bound is uniform. So n only depends on epsilon. And this is what makes it interesting as a combinatorial result, because in particular it tells us that if I have a sequence of finite graphs, I still have a partition of size which only depends on epsilon. So my graphs can be larger and larger and larger, right? But I always have the partition of the same bounded size, only depending on the error that I wanted to allow myself from the beginning. All right, so this is a partition result. And next time we'll see how this partition result can be strengthened in a very natural way when we restrict to stable structures or NIP structures or distal structures, etc. Where this kind of regularity lemma becomes exactly a typical result we want to prove in Sherlock's classification theory. But we know such results normally for types. So generalizing sometimes classical, sometimes not classical results from model theoretical classification theory, like Sherlock, neo-stability. If you generalize it from types to measures, they turn out to have exactly a content of this form, which tells you that you obtain a stronger form of the regularity lemma. And so, so I'll explain this next time. Several important cases of this. Okay, but I guess I'll stop here now. Yes, thank you very much.
Could you go back to the definition of definable measure?
Yes.
In the definition, you want some function to be continuous.
Mm-hmm.
Like in the standard definition of definable type, the condition of B being in the image of B being 1 is definable, but here it is type definable.
Yes.
Yes. So
yeah, that's exactly right.
Yeah. So there exists a measure where it is not definable but type definable only type.
Yes, that's typical. That's what typically happens. So so assume you have for which what you just said, this condition, let's say that the formula is in the type is definable. In other words, it means that the measure of this formula being 1, let's say, is a definable condition on the parameter. If it was only type definable, for a type, it would still be definable a posteriori because there are only two values, right? 0 and 1. So if both are type definable, it implies that each of them is definable then, because it's a type definable set and its complement is also type definable. Yes. But so typically, if you have, if your measure is allowed to take a continuum of values, like an infinite set of values, this argument wouldn't work. And in fact, yeah, basically any non-trivial example of a measure which is not a type, you will need it to be actually type definable as opposed to just definable. For a concrete example, I just take this, for example, the one we just did, like Lebesgue measure, and see why there you cannot get definability instead of type definability, for example. Yeah.
Okay, thank you.
Mm-hmm.
Hello, can you hear me?
Yes, yes.
So in general, it's not the case that the set of invariant Kisler measures form a closed subset of the whole space of Kisler measures, right?
It is the case. The set of invariant measures is a closed subset. Here is why. So look, like this condition is type definable. I mean, sorry, it's not type definable, but it is a closed set. So namely, I can look at the set of all measures mu measures over A, or sorry, let's say global measures, right? We want to define those which are A definable. So for this, the condition is going to be that I have phi of x A is equal to phi of xb, right? And I need to take it over all pairs AB so that they have the same type over A. So A has the same type as B over my set of parameters A. So this is a large intersection, of course. I have many pairs like this, right? But it is an intersection of sets, and each set of this form for the fixed pair A and B, this is a closed set.
Yep, makes sense.
Yeah.
Also, yeah, another question is, if I may, that you have these notions of A invariant and also definable notions that are from types. So you extend this to Kisler measures. You have also an analogous notion of finitely satisfiable Kisler measures.
Yes.
Right. Okay.
Yes, I haven't focused on it, but it will actually arise here in the next lecture. Yeah.
Thank you.
Of course. Yeah.
Do you know if there's any like counterpart of this Kisler measure theory, like for continuous logic, like definable sets but zero sets formulas or something like this, or maybe it's not interesting?
Sorry, could you repeat? If there's a counterpart of Kisler measures for what?
For continuous logic.
For continuous logic, yes, yes. It's actually not really. It kind of exists in the literature. It's not somehow written in one place. So there. In continuous logic, the natural thing to do is to consider measures as functionals by the what's it called, by this radon duality, right? So you should think about measures as functionals on the space of types, continuous functionals on the space of types, which corresponds to integration, right? So like each measure can be viewed as a linear function, as a function on the space of continuous functions. Excuse me, I might have said something earlier which made no sense. So a measure can be viewed as a linear functional on this on the space of continuous functions, where the value of this functional is the integral of that continuous function with respect to your measure, right? And so it's a classical result that this is an isomorphism, that this is the same thing. And so in continuous logic, then it's natural to view measures as continuous functionals on the space of types. And then the theory goes through in the same exact way. It is written partially in a couple of places. There's one place where it's written, I think recently, there's a paper by Pillai, Conant, and maybe someone else. I don't remember on the spot. If you email me, I can send you some reference. It's written there, and it's also written in some work that my student Aaron Anderson is currently working on. So yeah, one can say it kind of exists, but I guess it's not fully present in the literature yet. But yeah.
Okay, so if there are no other questions, let's thank Artem again.
Thank you.
And yeah, so now we have the coffee break, long one, but Jim is on time. Okay.